Welcome to this AI 101 video on case-based reasoning. I'm Tommy Thompson and you're watching AI in Games. In this video we're going to give a brief overview of case-based reasoning as a methodology. How does it work? Where and why is it used? As well as giving you a bit of understanding of where the interesting problems exist when building a system of your own. First up, let's explain what case-based reasoning is. Case-based reasoning, or CBR, is an automated reasoning and decision-making process whereby we solve new problems through the experiences we've accumulated in solving previous ones. This is achieved by accumulating data to build a model of understanding of a problem we're trying to solve. By storing the conditions of the problem and the actions taken at that point in time, we establish a collection of rules per se that dictate when in a given situation we have one or more actions to resolve it. The system is then focused on recognizing the similarity of new problems to existing ones, but also how to manage that collection of accumulated data. While we are interested in the AI methodology, case-based reasoning stems largely from the manner in which humans conduct problem solving and has correlations within cognitive science. We face a variety of decision-making problems in every day of our lives, but seldom worry about how to resolve them unless they are entirely new to us. If we are, for example, entering a coffee shop, we know how to get inside the building by opening the door. You don't question it given you've learned at an early age how to open doors, and as such, getting into the shop doesn't prove a problem. You just open the door and go in and order your coffee. The door might not look the same as other doors you've opened, but you understand that it's a door and know how a door works. Even if you're in a foreign country and don't know the language, you will approach the ordering of a coffee in much the same way you would do in your homeland. Given the way in which a barista and customer interact during the transaction doesn't really change when ordering in a different country. The hard part is overcoming the language barrier at specific moments. In this case, you made a judgment based on prior knowledge to order your coffee in Paris, Rome or Berlin in much the same way you would do in your favourite coffee shop in London. I have solved this problem before, so I will do roughly the same thing as last time and trying to work around the language barrier. The same principle often applies in video games, with specific tropes established throughout games such that we repeat actions in the same or different games with an intended outcome. If we have an enemy moving towards us in a platforming game, we'll often jump over or onto it. We build an understanding of when jumping on an enemy proves to be the best outcome versus jumping over it. When we meet similar, albeit not identical situations again in the future, we know how to tackle it. This is a critical aspect of how games are designed. We want players to memorize patterns of behavior that yield positive outcomes and make them repeat those patterns throughout the game in similar or different contexts. If this isn't properly established, the game can become confusing as we try to solve a puzzle that we're simply not prepared to deal with, as we've not had prior experience that reinforces our understanding of the problem we're facing. Case-based reasoning is a good method to apply when you have a situation that requires diagnosis, prediction, classification, or recommendation. As such, it has assumed a role in industries that has previously been covered by rule-based expert systems, a more rigid approach to the same problem that proved popular in the 1970s and 1980s. However, as we'll discuss later, CBR has effectively replaced them, given its ability to adapt and change its knowledge base over time. In addition, expert systems typically have a domain model, where some high-level language used to express data terminology in a set theoretic language. Case-based reasoning doesn't require data to be modelled in such a way and can be far more coarse and data-driven, ultimately being reduced to a bunch of numbers. As such, there are applications of CBR in situations such as medical diagnosis, vehicle fault diagnosis and repair, anticipating court outcomes based on legal precedents, and even fraud detection, given that in each case there is existing data that would allow us to identify what to do in a given situation, or at least give us a rough approximation of how to approach a different, albeit similar problem. Though perhaps the most common applications that people are familiar with is the recommendation systems that you see in the likes of Amazon and Netflix. In practice, CBR is focused on the management of cases, a set of pairings of a given situation or state X with action or decision Y. These cases are collated and stored over time, typically with the collection growing in size and scale. This collection of cases allows for us to build up more options for making decisions in given situations. We can then in practice use that collection to find actions to make by finding previously recorded situations that are similar to the one we're in now. So for this to work, case-based reasoning is structured as a 4-step process, sometimes referred to as the 4 Rs: retrieval, reuse, revision, and retention. Each of these phases interacts with the collection of cases, either editing the collection or retrieving actions from it to make. This means that the case collection is constantly being edited as the system is being searched for appropriate actions based on current situations, combined with updating it to highlight whether a particular case proved useful in a given context, as well as adding new cases when it seems clear that the current situation has little relation to anything we've already stored. So to cover the 4 R's in a little more detail, let's walk through each of them. Retrieval is the process of finding a case that is similar to our current situation or state. This relies on an ability to assess a given state on its applicability to the current one. We'll come back to this in a minute. Reuse is when we retrieve a case and propose it as a valid action to apply in our current state. Revision is when we evaluate through a series of metrics or even simulations how well this proposed action will perform and whether it's practical to apply it in the particular case we're in. This sometimes results in some revision of the action to fit the current context. Then lastly, retention is applied after a successful execution by storing the result of this experience in the case system. This is useful when we revise the proposed solution, given it's now clearly an individual case. These 4R methods provide a decision-making system that can generalize its previous experiences, allowing you to apply decisions made in similar but not identical circumstances to new situations. Coming back to the coffee shop example, you can continue to open that door and order your coffee irrespective of where the door is in the layout of the coffee shop because it's roughly the same problem each time. We've successfully generalized this problem. Even when the situation differs, like you're baking different types of cake, you can often apply the same rules to get your desired outcome, given once again you've generalized that problem. The secret sauce is how the model is stored and your metrics for comparing cases in the system, as well as comparing cases to the current state of your problem. We would typically store the states of our case spaces as n-dimensional real vectors, or rather, one or more collections of real numbers. This is useful given it allows you to quickly run similarity measures across two distinct cases to check whether they're compatible with one another. These similarity measures often act like heuristics in classic AI search, given they're applying expert knowledge against the dataset to infer some understanding of their similarity in a given problem. But even with the similarity measures, there are still lots of small nuanced issues that need to be addressed. How to tweak cases that are not 100% fit for the task at hand, when to add new cases or delete old ones, and tweaking the similarity measures being used. This is where techniques such as machine learning can be applied to automate that process and save the life and soul of a poor human subject expert who would otherwise have to do it all manually. As such, you could craft an ever-growing and adapting system that learns from experiences over time. And that's it for this AI 101 on case-based reasoning. If you're keen to see how this can be applied, check out my case study on how Killer Instinct's Shadow AI clones a player's behaviour and replicates it in a non-player character. I'm Tommy Thompson, and you've been watching AI in Games, a series in artificial intelligence supported on patreon.com. If you found this video useful, head on over to patreon.com/AI_and_games and find out more about our content. Thanks for watching.